stuff up and see at what point students will question it. The fear, though, is that no one ever questions it. I get through an hour and 15 minutes, and then someone said, "But you said." It's like starting a cult. I can stop it. And by the way, there was a documentary on someone who started a cult and talked about his having to eventually tell them that he was making a living out of it.
How'd that go for him?
A couple of people just walked out, really ticked off. Others were just confused, angry, hurt. He was able to resolve it with some of the people, but not everyone.
He's like, sorry, the joke went too far.
Yeah, it started out as a curiosity.
It was just a prank. The prank created a cult.
All right, anyway. So, I introduce you to the parallel axis theorem. Now, as you might guess from the title, we're talking about an axis which is parallel to an axis going through the center of mass. Okay, some of that you might not have guessed, but the fact that there's a parallel axis is very important here. So if I have a disk, rotating about a normal axis through the center of mass, that moment of inertia, and I'll just put a little cm, is 1/2 mr squared, where that's the radius and some mass. Just a side note, thickness doesn't matter. I call it a disk. I could also call it a cylinder. There's mathematically no difference.
So when we were talking about point of contact, nay.
Oh no, I'm going to connect it back to that. That was not just an arbitrary, let me just drop this truth bomb and then move on.
Oh, okay.
I'm going to explain the rationale behind what I did.
Well, okay.
And we'll see who just walks out.
Got it.
All right. Well, if we time it right, all of you will walk out. So, if instead this were, instead of rotating about the center, it rotated about an axis here, parallel to that axis. We have this axis through the center of mass. We have this axis we just basically moved that way, a distance r. Doesn't have to be a distance r, just move to some other spot. The parallel axis theorem is that the moment of inertia about some axis p is equal to the moment of inertia about the center of mass plus mass times h squared, where this h is the distance between the parallel axes. I guess I should say center of mass, axis, and parallel axis.
Distance, but what is that second word?
Twixt.
Twixt. Between.
Betwixt. I think it comes from betwixt, which is a Shakespearean thing, or I could just be making this whole thing up. I didn't feel like writing out between.
But it means between.
Yeah. I'm sure with the millions of people who will watch this video later, someone will correct it. All right. So yeah, that means that in this case,
I watched
I have 200 something subscribers, so I'm not sure why. All right, anyway. Moment of inertia about point P would be the moment of inertia about the center of mass, so 1/2 mr squared, plus the mass times how far we move the axis, which was r. So the moment of inertia about this point, so if I were, instead of rotating about the center, I was rotating about this point on a point right there, moment of inertia would be 3/2 mr squared.
3/2.
Question.
Yes.
So that means that because if you're rolling down a hill, you're constantly changing
The axis of rotation.
the axis of rotation.
Yes.
So then I feel like there's some sort of constant or some sort of formula for that.
I think we're getting to that, and it's possible we'll get there and you'll go, that's not what I was talking about, but
Oh, no, that.
let's finish this off and see if
Yeah.
we get you there.
Fine.
So, if I'm looking at this object right here, I would say that the kinetic energy is 1/2 I omega squared, where this is omega rotating about this point of contact right there. Because that's the axis. If this is rotating about that point right there, so I have some distance r there to the radius, that means that the center of mass, the speed of the center of mass, is equal to that omega p times the radius. So this is rotating about that point at that instant, at that speed.
So for that equation, the k equals 1/2 I alpha omega squared. Is that k, I assume it's different than kinetic energy?
Oh, the one I was using, this is kinetic energy.
Look at that, that's just the formula for.
Yeah, this is when we derive the formula for kinetic energy for an object where a
Mhm.
rigid body is rotating.
Okay.
We came up with that. I here is the moment of inertia about this point P. So by the parallel axis theorem, this is 1/2 times the moment of inertia about the center of mass plus m times how far we move the axis. We move the axis from the center of mass down to here times omega p squared. So I have 1/2 I center of mass omega squared plus 1/2 m omega squared. Sorry, write that order. R squared omega squared. So just distributing the half and distributing the omega. That is that's the rotational kinetic energy about the center of mass, which is what we used. And this, well, I've got r squared omega squared, which is just v squared of the center of mass, which is the linear kinetic. So this is what I was labeling as the rotational kinetic, and this is the translational kinetic, or linear kinetic. And I just started with that. But that's justified that when you have an object rolling down an incline, if it is indeed a perfect roll, then yes, the axis of rotation really is that point of contact. However, we can treat it as the kinetic energy of an object rotating about its center plus the linear kinetic. So the justification for what I had done. Did I answer your question or your concern, Ibrahim?
So how does that take into account so when we're looking at graph, when we're looking at a problem, it's only concerning instantaneous.
Yeah. In reality, yes.
Got it. Because I was thinking, like, if we're taking into account all of the, I was like,
We have an infinite number of infinitesimally small things.
wait, didn't we say we had something before that? Infinite number of.
Calculus.
Oh, yeah.
And after class on Tuesday, I was going through the derivation of using calculus for the derivation of the solid sphere. And I know Carolyn was there, and were you there also watching?
I saw the inspirations of it, but it all looked like Arabic to me.
Okay.
Actually.
I realized what my boneheaded mistake was, so, and I was gonna show Carolyn, but she decided to snub us.
But I did get to, I understood where you were going.
Yeah.
Where did you go, like, in essence, where did you make a mistake?
If I have a solid sphere rotating about its center, the distance r is not from the center, it's from the axis. So only these 2 points, if it's spinning about this point, only this point and this point are the radius away. I needed to be looking at this distance, not that distance.
That was a good demonstration.
It was just absolutely beautiful hand gestures,
So,
and it's recorded for all time.
in a sphere, the axis is, there's only one axis to it?
Yeah, if I have an object spinning about its central axis here,
Right.
actually, let's go for a three-dimensional effect. Absolutely spectacular. I know what you're thinking. You're going, hey, wait a second. Did you go to art school? No, but my grandmother did. All right. If it's spinning about an axis here, and you could be so bold as to have yet one more color. If it's spinning about that axis, then R, because it's the sum of all the MIRI squared, R is this distance.
Okay.
That was the, it's not from here to there and there, there, it's not that. That was the bonehead mistake.
Because it's spinning here.
Yes.
It's not concerning everything else, it's just these two. Or like you
Just-
said, because
just-
it's.
It's, it's the direction normal to the axis.
Yeah. Right words.
Anyway, and on that controversial note, if there are any questions, ask them on your way out, or you can just ask them right now to board them out, or have a wonderful weekend. Those are your only two choices. So if you ask a question, the wonderful weekend's out the door.
Well, here we go.
Let me go ahead and stop this, unless you want the world to revel.
What, how come we're